Hello class, it's Mr. Mormon again. Today we're going to be learning about the periodic table and how to draw models of atoms. Now to start with, let's look at a couple different periodic tables. In class I gave you two different periodic tables, and I did that for a reason. The periodic tables that you're going to find in different books may be arranged in different ways. The one that I have hanging up in the classroom is a little bit different than the two that I've shown you. Now here's one. And here's the other. I usually use this one because the numbers are a little bit larger and it's a little easier to see. They both contain the same information. It's just displayed in a different way. Now the key to figuring out a periodic table is to look at the key. When you look at the top or side of any periodic table, there's going to be a key that tells you what all of the numbers represent, all the numbers and letters. In this periodic table, just below the symbol, you're going to find the atomic number, and above it is the atomic weight. You got an electron configuration and the name of the element. Switching back to this periodic table, you can see that we have the same information, but it's just displayed a little bit differently. The atomic number is in the upper left-hand corner. The atomic weight is down at the bottom, but here it's not rounded. You're going to have to do the rounding yourself. The electron configuration in this periodic table is up in the upper right-hand corner. Same information, just displayed a little bit differently. Now let's talk a little bit about how the elements are arranged here. You'll notice that there are numbers. The atomic number is how the elements are arranged. Hydrogen is number 1, helium number 2. And they increase from left to right and from top to bottom. Left to right and top to bottom. So just like a book, you would read across and then down. Now, elements that are in the same column would be called a group or a family. All of the elements in a group or family are going to have similar characteristics because of their valence electrons. Those are the electrons are on the very outside, on the outer energy level of the atom, and those are the ones that will interact with other atoms around them. In the outer level, all these atoms or elements have the same valence electrons. So they're going to react in a similar way. Each column would have similar chemical properties. Again, those are groups or families. Now, if you look at a row across the periodic table, that's called a period. Now, if we look at this period, this is period 2. There are 8 elements that make up this second period. And these are the 8 elements that make up that period. And they're in order. And what we see here is called a Lewis dot diagram of each one of these elements. And they show the free, the valence electrons, the electrons that are in the outer energy level. Now, neon at the end of the period here is full. 8 is a comfortable amount of electrons to have in the outer energy level. And we can see that it's got 8, so there's no room for any other electrons. Fluorine, however, is missing one in this spot right here. So fluorine likes to react with other elements to gain the electron that it needs. Oxygen is missing 2, so it's going to make 2 bonds. Nitrogen 3, carbon 4. At the other end of the period, these elements find it easier to lose the electrons that they have to other elements, and that's the kind of bonding they make. I mean, lithium would have to gain 7 electrons to fill its outer energy level, and that's a very difficult thing to do. But if it just loses this one, then it's to a comfortable state. This is called the octet rule, where elements try to get their outer energy level to a stable 8 electrons. Now neon, like I said, because it is already full, doesn't like to make any bonds at all. And it belongs to a group, if we go back to the periodic table, we can see that, called the noble gases. Here's neon on this periodic table. This whole group or family would be the noble gases. And like I said before, each family has similar characteristics. because they're all in the same column here, they're going to have similar characteristics. They all are full in that outer energy level with 8 valence electrons, so they don't like to make bonds with anything else. In other words, they're like nobility. They've got their noses in the air and they do not like to associate with the other elements, and therefore do not become part of compounds. Helium's a little bit different. Its outer energy level is full, but it only has 2 electrons, but that's the first energy level, which can only hold a maximum of 2 anyway. So that one's full, just in a different way. Another important thing to note about the periodic table is the lanthanide and actinide series, which are down here at the bottom. These 2 long series actually belong right in here. If you look at the numbering, and see how the periodic table kind of steps down with these kind of blank spaces in between. There should be another large blank space right here over the actinide and lanthanide and actinide series, but then that would make the periodic table so wide that it would be hard to print. So what they do is chop this section out of the middle, print it underneath, and just show where it belongs. It actually belongs right in here. Okay, let's do a quick review of what we've already learned about the structure of an atom, and then we'll get into drawing models of atoms using the information from the periodic table. Okay, to start with, there's a very dense center in the middle of the atom, which we call the nucleus. Now, it's important to note that this word nucleus is used also when we're talking about the center of a cell, which is, it acts kind of like the brain of the cell. It's the control center. And it's also normally found at the middle of a cell. Here, of course, we're talking about the nucleus of an atom, which is much, 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 much smaller than cells. As a matter of fact, cells, just like everything else, are made up of atoms. Now, the reason that we use the same word nucleus, it goes back to Latin. Nucleus means core or center, so you can see why we use the same word to represent the nucleus of an atom and also the nucleus of a cell. Be sure you don't mix the two up. Now, the nucleus contains smaller subatomic particles called protons and neutrons. The protons have a positive charge, neutrons are neutral or have no charge. Now, zipping around the outside of the nucleus are electrons. Electrons have a negative charge. They have very, very little mass. As a matter of fact, it would take over 1,800 electrons to equal the mass of 1 proton. So they really do not add much to the mass of the atom. But they still have lots of energy, and they have a negative charge. Those are a couple things to remember about them. And they zip around in that mostly empty space outside the nucleus, and they define the area or volume of the atom itself. Okay, let's draw some models of atoms like we will do in class. Now, there's 3 simple rules to remember when drawing atoms. First, the number of protons is going to equal the atomic number. And remember, that's how the periodic table is arranged, by the atomic number. The atomic number, or number of protons, is really what identifies an atom. Now, to figure out how many neutrons are in the nucleus, it's going to be the atomic weight minus the atomic number. Now, it's important to understand why this little formula works. Protons and neutrons each have a mass of 1 AMU. That's the units that we use for the weight of the atom. Figuring out the atomic mass or weight, those are in AMUs, which are atomic mass units. Protons and neutrons each weigh 1. Now, like I said earlier, electrons have almost no mass. So they really don't count in the mass of the whole atom. So the atomic weight is really the weight of the nucleus. Now, if each proton and neutron weighs 1, the atomic weight is the weight of the whole nucleus. If you subtract the atomic number, which is the protons, what's left over would be your neutrons. So that's why that little formula works. Atomic weight minus the atomic number, which is basically the nucleus minus the protons, would give you the number of neutrons. And finally, the number of electrons is going to be the same as the number of protons. So that would be the same as the atomic number, of course. You can look at the electron configuration on the periodic table to figure out which energy level those electrons are in. So let's see what that looks like. So here's my periodic table again, or one of the versions that we've been using. Let's just pick an element to draw. You know what, let's do carbon, which is right here, which is also the one that they usually use for the key. Okay, so here's my information from the periodic table for carbon. I can see the atomic number, the atomic weight, the electron configuration. That's all the information I need to draw this element. Let's start with the protons. Again, remember the protons are going to be equal to the atomic number. Here I see it's 6, so I've got to draw 6 protons. There we go. You'll notice that I put a little plus sign in each one because, of course, these are protons and they have a positive charge. Okay, to complete the nucleus, we have to put the neutrons in there. Now take a look back here in the box with the information on carbon. I see the atomic weight is 12. That's the weight of the whole nucleus. Now there were 6 protons, so 12 minus 6 is 6. There's going to be 6 neutrons, and I can draw those in as well. Okay, there's my completed carbon nucleus, 6 protons, 6 neutrons. I put an N in the neutrons to represent their neutral charge. They have no charge. Now to finish this up, I have to put in my electrons. As we saw in the notes, the electrons are going to balance with the protons, so I'm going to have 6 electrons, and I can see from the electron configuration up here in the box, it's 2, 4. That's translated to mean that there's 2 electrons in the first energy level and 4 in the second energy level. So here's my first energy level with 2 electrons, and here's my second energy level with its 4 electrons. Notice that I put a little minus sign in each one of these electrons to represent their negative charge. Also remember that in this model, it kind of looks like the electrons are going around in an orbit, like the planets go around the sun or the moon goes around the earth. And that's not really true. As we learned in the last video, the electrons, you can't even actually predict where they're going to be. They do not follow a single path. There's a probability of where they're going to be located, and that's called an orbital. And it would look like, you know, kind of like a fuzzy cloud. They often call it the electron cloud, where these electrons would be zipping around the nucleus. They're not following a single path, which this model, it's one of the shortcomings of this model. It kind of makes them look like that. Another thing to note is that in actual size, the nucleus would be much, 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 much smaller than this. And the atom itself would be, you know, 99.9% empty space. The nucleus would be a tiny dot in the center, and that's where all the mass would be concentrated, and then the even smaller electrons would be zipping around outside. Now, here's a shorthand method to draw or to represent the subatomic particles in an atom, and this would be how you would draw carbon, where the circle represents the nucleus with its 6 protons and 6 neutrons, and these represent the energy levels. The first energy level with its 2 negative electrons, and the next energy level with its 4 electrons. Okay, let's do another quick one. Just before carbon on the periodic table is boron. Here's the information box for boron, and that's all we need. It's got all the information we need to draw a model of boron. Why don't you pause the video here for a minute and do your drawing of boron, and then check it with mine in just a minute. Okay, is this what you ended up with? You should have 5 protons in the nucleus. 1, 2, 3, 4, 5. You should have 6, again, the protons we get from the atomic number. 6 neutrons. The atomic weight is 11. 11 minus 5 is 6. So we've got 6 neutrons. Electron configuration is 2, 3. So I've got 2 electrons in the first energy level and 3 in the next energy level. It's important to note here that the protons and neutrons are not always going to be the same. The protons and electrons will always be the same number because the elements are electrically balanced, the pluses balanced out with the minuses. But the neutrons are not always going to be the same. They were the same in the carbon atom we did, but you see here they're not the same with 5 protons and 6 neutrons. They're not always going to be the same number of neutrons as protons. To draw this shorthand, it would look like this. With 5 protons and 6 neutrons in the nucleus here, 2 electrons in the first energy level, 3 in the next energy level. Okay, that should be about enough of a tutorial on how to draw atoms. You can use the exact same method to draw any element on the periodic table. Obviously, the bigger ones are a little bit more difficult to draw, but you'd follow the exact same methodology to draw an element from further down on the periodic table. One last thing, the energy levels do have a maximum number of electrons that can go in each energy level. The first energy level, you will never find more than 2 electrons in it, like we see here. The next energy level can hold up to 8, the next energy level up to 18, and it goes up from there. The 4th energy level can hold up to 32, as can the 5th energy level. And it gets kind of weird after that, the outer energy levels. But the main point is that the inner energy level can hold 2, and then they spill over to the next energy level out, which can hold 8. And then they spill out from there if that energy level fills up. If they fill up from the inside to the outside as you move down the periodic table and across. The lower energy levels on the inside fill up first. All right, that's about it. We will see you tomorrow in class.